Welcome. In this session on natural deduction, we'll explore the semantic of predicates. For this and for all of our sessions in semantics, we're going to assume that the universe of discourse is a non-empty set. Let's recall how in natural deduction we write a predicate. We might write a predicate that has one argument as P, or perhaps we would write it as Q. If a predicate has two arguments, we might write it as a relation, and we might write it in this way. And if a predicate had three arguments, we might write it in this way, and so on. Now, when we turn to the semantics, what we'll have to do is we'll have to specify it. And there are two widely accepted methods. The first is called intentional. And that is, let's put this in quotes, and that's what we intend. And this is a rule, or better, we can say, because we're working in a metalogic that has set theory, we can say it's a map. And so let's explore what we mean by a map for a predicate that has one argument. We might say that a predicate in general is a map, and it takes a term, that is, it takes a literal, it takes a function, etc., and it maps, the range of it is T and F. And this is a general idea, and it requires complicated work in a set theory to operate. What we'll do instead is we'll use the other method, which is called extensional. And that is what the predicate is what it extends to. And this is a set. So, for example, we might say that a predicate in a particular model will be a set of, for example, 0, 2. Now, this only makes sense once we've specified the universe of discourse. So that's why we usually begin by saying, what is the universe of discourse? What are the objects that a term can range over? And then we'll specify this. Now, how are these the same? Well, ultimately, if you have a rule and you apply this rule to terms and these map to T, then you would say that the domain of this predicate that maps to T is this set. And so you could begin with the rule and you would end up with a set, or you could begin with the set and you'd end up with a rule. And each of these make sense. Each of them is possible in a set theory metalogic. We'll work with the extensional definition. This has two advantages. One is it lets us easily talk about small problems, and the other is that when we go to implement something like natural deduction and we apply it to computer programs, if we're defining a predicate as a set, we can do a very quick check. That is, if we're given a term, what we do is we say, is that term in the set for the predicate? If it is, it evaluates to T. If it is not, it evaluates to F. Let's take an example. Let's suppose that our universe of discourse is the numbers that we need in base 4. So that will be 0, 1, 2, and 3. And we could then define the even numbers within this model as being 0 and 2. and we could then define the odd numbers in this model as being 1 and 3. And this would now allow us to make statements that aren't true in general, but are true in this model. For example, we could say that every object is either P or Q. How would we write that? Well, we would write that as for all x, x is in the set P, or x is in the set Q. And this is easy to write and it's easy to check. So within this model that has this universe of discourse and these two predicates, we're able to define this easily. This idea extends to relations and to higher order ones, because what we would do is we would say, for example, that we would define R in a model, and now instead of having individual objects from the set, what we have to do is have pairs. So we might, for example, have a pair 0, 1 in the set. We might have a pair 1, 2 in the set, and we might have a pair 2, 3 in the set, and there might be no other sets. And if you think about this for a moment, you can probably come up with a relation that R represents. And it would be, for example, the relation x is strictly less than y. And you could either define that intentionally by having a complicated map, and in set theory it may not be immediately clear how to formulate that, or we could simply write down, for this limited universe of discourse, we could write down the set of all pairs that that relation holds. So this is what an extensional definition of a predicate is. So sometimes when we're going through semantics, what we'll do is we'll say the predicate is the set. And when we say that, what we mean is it is indistinguishable whether we use a set to describe a predicate or whether we use a map to describe a predicate. They both end up at the same place, and we'll prefer to specify a predicate as a set.